सिंपल सा क्वेश्चन था कि व्हाई डज अमोनिया फॉर्म हाइड्रोजन बॉन्ड्स बट PH3 डज नॉट. दिस इज द क्वेश्चन, राइट. अब देखो, इसमें सबसे पहला पॉइंट ये है कि जो इलेक्ट्रोनेगेटिविटी है, इलेक्ट्रोनेगेटिविटी ऑफ नाइट्रोजन इज, electronegativity of nitrogen is 3.0 and electronegativity of hydrogen is 2.1. So because of this difference in electronegativity, NH bond is polar. So as NH bond is polar, so what it means that nitrogen acquire partial positive charge and nitrogen acquire partial negative charge because of higher electronegativity, and hydrogen acquire partial positive charge due to lower electronegativity, right? So in this way, in ammonia, nitrogen has partial negative charge, hydrogen has partial positive charge, and that's why it will attract the nitrogen of the other ammonia, and the bond between hydrogen of the one molecule and nitrogen of the other molecule, this interaction is called hydrogen bond. So there is a hydrogen bonding between ammonia molecules. Okay, but now come to PH3. So in PH3 there is a phosphorus and hydrogen. Electronegativity of phosphorus is 2.1 as well as hydrogen, it is also 2.1. that means pH bond is non-polar. So see, pH bond is non-polar, NH bond was polar, right? That's why PH3 does not form hydrogen bond. Got it? There is a simple case, and when hydrogen is attached to phone, FON, what is the condition of the atom attached? Which is more electronegative and small in size. Hydrogen is attached to an atom which is small in size and higher in electronegativity, and these two conditions are satisfied by only three elements, that is fluorine, oxygen and nitrogen, which can form hydrogen bond. So H2O, HF, NH3, they can be associated through hydrogen bonds, but PH3 does not have such condition because phosphorus is large in size, it is less in electronegativity, and at the same time its electronegativity is same as that of hydrogen. That's why pH bond is non-polar in its nature. That's why PH3 does not form hydrogen bond. Very simple question. Okay, next question is, how is nitrogen prepared in the lab? Simple question. How is nitrogen prepared in the lab? And write the chemical equation of the reactions involved. Okay. So, nitrogen, preparation of nitrogen in the lab, or we can write it as laboratory preparation of nitrogen. So to prepare nitrogen in lab, first of all we should have ammonium chloride. Ammonium chloride, when react with sodium nitrite, we get ammonium nitrite along with NaCl. by double displacement reaction. See, it is a double displacement reaction. As in ammonium chloride, there is NH4 plus and Cl negative. Sodium nitrite, there is Na plus and NO2 negative. So NH4 plus is attached to NO2 negative and we get ammonium nitrite. We get ammonium nitrite along with NaCl. Okay. Now this ammonium nitrite, this can be easily decomposed and we get nitrogen gas, okay, along with 2H2. So in this way, nitrogen can be prepared in the lab and these are the chemical equations involved. So first of all, we should have mixture of ammonium chloride, aqueous solution of ammonium chloride. When mixed with aqueous solution of sodium nitrite, we get ammonium nitrite. And when ammonium nitrite is it is easily decomposable, there is no need to heat even, it is easily decomposable and we get N2 gas. And to prepare N2O, nitrous oxide, simple method is just convert sodium nitrite into sodium nitrate. If we have sodium nitrate, we get ammonium nitrate, right? Instead of sodium nitrite, if we have ammonium nitrite, we get N2O along with H2. Very simple. They are actually connected to each other. That's why I write here. Sodium nitrite gives nitrogen gas and ammonium nitrite gives nitrogen gas and ammonium nitrate gives nitrous oxide. Okay. Now, next question. Question number 7.6. How is ammonia manufactured industrially? Means industrial preparation of ammonia. Industrial preparation of ammonia, or we can say commercial preparation of ammonia. So commercially it is prepared by which process? Yes, tell me. I think everybody knows by which process we can prepare it. Yes, tell me. Which process is used to prepare ammonia gas? So it is even in equilibrium chapter in class 11. So commercially, yes beta, commercially ammonia is prepared by, yes beta, it is prepared by Habers process. Which process? Habers process. And what is this Habers process? N2 gas react with H2 gas to give NH3 gas. N2 gas react with H2 gas to give NH3 gas. So this is the reaction. 1 mole of N2 gas react with 3 moles of H2 gas to give 2 moles of NH3 gas, and reaction is exothermic. For this reaction is exothermic. Value is I think almost minus something. Just write negative. That's it. Reaction is exothermic. So first of all, effect of temperature. So as reaction is exothermic, so exothermic reactions are favored at low temperature. But if temperature is very low, reaction is very slow. Why? Because there is a N triple bond N, and nitrogen is unreactive or inert at room temperature. So an optimum temperature is required. An optimum temperature of 700 Kelvin is required. An optimum temperature of 700 Kelvin is required for the reaction to take place. Okay. Next, effect of pressure. Effect of pressure. So if you see on the reactant side, how many moles are there? There are 4 gaseous moles. On the product side, there are 2 gaseous moles. That means forward reaction is favored by decrease in gaseous moles. Number of moles decreases on the product side. So according to Leach-Atellier's principle, high pressure favors that side of the reaction where number of gaseous moles are less, where number of gaseous moles are less. So product side number of moles are less, so high pressure, and high pressure of the order of 20 megapascal. High pressure of the order of 20 megapascal favors the formation of ammonia. So first is optimum temperature, not low. Keep in mind, though reaction is exothermic, but if temperature is very low, then the rate of the reaction is very slow. Reason being, N2 is unreactive or inert even at room temperature. So an optimum temperature is required. What do you mean by optimum? Optimum means it is like this: rate versus temperature. If you plot the graph, then with increase in temperature, rate increases and it reaches a maximum and then it decreases. So this temperature at which rate is maximum, that is called optimum temperature. Means optimum temperature is 1, below it or above it, rate is slow, rate is less, okay, and maximum at that temperature, particular temperature, that is called optimum temperature. Okay, means it cannot be more than that by increasing temperature or by decreasing temperature. Okay, if we increase the temperature, rate is slow down. If we decrease the temperature, even then it slows down. It is maximum at that point only. Okay, now third one is effect of catalyst. Reaction is reversible. Okay, so even at 700 Kelvin, rate of reaction is not very high, so catalysts are required. We need catalyst. So catalyst used is iron oxide along with potassium oxide and Al2O3. This mixture is used as a catalyst, and sometimes we use molybdenum. It acts as a promoter. What is the use of promoter? Promoter enhances the activity of the catalyst. Promoter enhances the activity of the catalyst. It has nothing to do with the reaction. It only make catalyst more effective. Means it brushing up the catalyst only. Promoter has role only if catalyst is present. It has nothing to do with the reaction itself. Okay, it is not affecting the reaction directly. It enhances the activity or efficiency of the catalyst, which in turn increase the rate of reaction. Done. So these are the three factors. Sometimes question is, what are the conditions to get maximum yield of ammonia? So these are the three conditions: optimum temperature, high pressure, optimum temperature of the order of 700 Kelvin, high pressure of the order of 20 megapascal, and presence of catalyst, that is iron oxide, potassium oxide, and third one is aluminium oxide. And sometimes we use even promoter, that is molybdenum. Okay, so if we draw its flow chart, so it is like this. See, first of all we have N2 gas, H2 gas, then there is a pump which maintain pressure of the order of 20 megapascal. Okay, then there are catalysts. This mixture of N2 and H2 at this 20 megapascal pressure that is applied at by the pump, then it comes in contact with Fe2O3, K2O, and Al2O3. So it leads to the formation of N2, H2, and ammonia. And that N2, H2, and ammonia now at high pressure, that gas is released, and therefore from high pressure it becomes low pressure, and therefore here ammonia is liquefied. There is liquid ammonia. Now rest of the things, that is leftover N2 and H2 further goes back same. There is a again pump, it sucked the nitrogen and hydrogen, and therefore it further mixed. Means this circle continues till whole of the N2 and H2 is converted into ammonia. So this is flow chart for the manufacturing of ammonia. What we do, first N2 gas and H2 gas, they are inserted into the pump which is maintained at 20 megapascal. Then that gas mixed with these catalysts which is in the chamber which is maintained at 700 Kelvin, and therefore N2 and H2 react to give ammonia gas. Okay, Madhur and Gaming Panda, Raj, thank you, beta. So we get ammonia and along with N2 and H2. So ammonia, because if we compare N2, H2 and ammonia, ammonia is associated through hydrogen bonding. N2 and H2 are non-polar. So there is a strong bonding, hydrogen bonding between ammonia molecules. Therefore, it is liquefied when it is released from high pressure to low pressure. And therefore, ammonia is liquefied, but N2 and H2 gas, it remains in the gaseous state and it goes back because there is a pump which sucks the gas, and N2 and H2 that goes back to the pump at high pressure and therefore again mixed with catalyst, and therefore leftover N2 and H2, further equilibrium is maintained, ammonia gas is formed. This process continues till whole of the nitrogen and hydrogen that is converted into ammonia. This is the flow chart for the manufacturing of ammonia. Okay, now next one, illustrate how copper metal can give different products on reaction with HNO3. So keep in mind, copper when react with dilute HNO3, then we get copper nitrate, or we can say cupric nitrate, along with NO and H2O. We get nitric oxide. And if copper is mixed with concentrated nitric acid, then we get copper nitrate along with NO2 and H2. So just balance it. Balancing is more important. See, now in this case, to balance this equation, I can write here copper, you can write HNO3 two times. Wait 1 minute. Oh my god. Okay. So copper and HNO3, you should write HNO3 two times. Why? Because some copper is in the form of nitrate only. Sorry, some HNO3 is in the form of nitrate only, and some in the form of NO. Okay, so copper is in zero oxidation state. Here copper is in +2 oxidation state. HNO3 in +5 oxidation state. Here it is in +5 state, but on the other side it is in the +2 state. Okay, so copper 0 to copper +2 means increase in oxidation number by 2, and second is HNO3 +5 to +2 decrease in oxidation number by 3. Okay, so we multiplied by 2 and this one by 3. So 3 copper and 2 HNO3. So when 3 copper are there, copper nitrate are 3. So this is nitrate. So 3 to the 6, 6 HNO3. That means it is 3 copper plus 2 plus 6, 8 HNO3 to give 3 copper nitrate along with 2 NO. And how many H2O? See, out of 8, there are 4 H2O. So that's it. This is the balanced chemical equation for dilute HNO3. Now, if we compare for concentrated, so see, to have this copper solid plus HNO3 concentrated. So again, you should write it 2 times to give copper nitrate along with NO2. Okay, so now see, again copper 0 plus 5 plus 5, here copper plus 2, nitrogen plus 5, nitrogen plus 4. So from copper to copper 2 plus, increase in oxidation number by 2. Now HNO3 decrease in oxidation number by only 1. Decrease in oxidation number by 1. Okay, so that means it should be multiplied by 2 only. Simple. So just multiplied by 2. So 2. So in this way it becomes copper plus, and how many NO3? Twice. So 2. That means 4 HNO3 concentrated to give cupric nitrate plus 2 NO2 and how many H2O? 2. That's it. So in dilute HNO3, we get nitric oxide, and with concentrated HNO3, we get NO2. Beta, I put it on charging. Okay, give resonating structures of NO2 and N2O5. So see, in NO2, NO2 is an odd electron molecule. NO2 is an odd electron molecule where it is like this. Structure is like this. And there is a resonance where coordinate bond is on the right or left. It can also be written as, to replace this coordinate bond, nitrogen should have positive and oxygen should have negative. Nitrogen positive, oxygen negative. So this is NO2. Now come to N2O5. So in N2O5, its structure is like this. This one or like this. Or coordinate bond can be replaced by covalent bond. Okay, but then nitrogen should get positive charge and oxygen should get negative charge. So there may be a question, in N2O5 is there any NN bond? So there is no NN bond because oxygen is in between two nitrogen atoms. Okay, so this is question number 8, 7.8. Now 7.9, the HNH bond angle is higher than HPH, HASH and HSBH angles. Why? So there is a simple reason. First of all, just write the shape. You know, in NH3, there are 3 bond pairs and 1 lone pair. There is 1 lone pair and 3 bond pairs. So this lone pair repel the bond pairs. And you know, according to Vesper theory, lone pair bond pair repulsion is greater than bond pair repulsion. So hybridization of nitrogen is sp3. Why? Because it has 3 bond pairs, 1 lone pair. So total pairs are 4. So hybridization is sp3. So normal tetrahedral angle is 109 degree 28 minute. But because of the presence of lone pair at one of the apex, at one of the tetrahedron, these bond pairs come closer and therefore bond angle is 107.8 degree. Okay. Now, you know, nitrogen is most electronegative among group 15 elements. So bond pair is closer to nitrogen. So here bond pair repulsions are maximum in comparison to phosphorus, arsenic, antimony. You know, nitrogen is less electronegative, so bond pair moves away from it. In ASH3, bond pair is further away from it. In SBH3, it moves further away from central atom. Therefore, bond pair repulsion decreases. Bond pair repulsion decreases. So as bond pair repulsion decreases, so bonds come more closer and therefore bond angle decreases. So bond angle in case of pH3 is around about 93.6 degree. In case of ASH3, it is around about 91 point, I think 8 degree. Just for the sake of comparison, I am writing 91.3 degree. Wait, I will check if it is like that only. Yes, it is 93.6 degree, 91.8 degree, 91.3 degree. So you can write as electronegativity, or you write on this side as electronegativity of central atom decreases. So bond pair moves away from central atom. Bond pair moves away from the central atom. So bond pair bond pair repulsion decreases. Bond pair repulsion decreases. So bond angle decreases. That's it. Okay. But any doubt up to this? Yes, Saad, from 8th August. Why does R3P double bond O exist, but R3N double bond O does not? Because phosphorus has vacant d orbital. Phosphorus has vacant d orbital, so it can form p pi d pi bond with oxygen. Phosphorus has vacant d orbital, therefore it can overlap with oxygen by p pi d pi bond. It forms p pi d pi bond, but nitrogen does not have vacant d orbital. You know, nitrogen does not have d orbital. Therefore, nitrogen cannot expand its covalence beyond 4. So here, if you see, there are 5 bonds. So nitrogen cannot form pi bond, a 5 bond, sorry. Nitrogen cannot form 5 bonds, and at the same time, nitrogen cannot form p pi d pi bond. That's it. Okay, so that's all for the day. Thank you so much for watching this video. There is class daily from 8 p.m. to almost 8:45 p.m. So do join the class, and we are covering NCERT exercise first of P block elements. Then we will start D and F block elements. Okay, thank you so much.